Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today, we have the pleasure of presenting a public lecture by Professor Jocelyn Reed, who is a professor of physics at California State University, Fullerton, and currently a visiting fellow at the Perimeter Institute. Professor Reed received her PhD from the University of Wisconsin-Milwaukee in 2008. Her research work includes dense matter modeling in neutron stars, predictions of gravitational wave signals from neutron star mergers, proposed mechanisms for precursor flares in gamma ray bursts, new methods for gravitational wave cosmology, uncertainty quantification for neutron star merger source modeling, and measurements of dense matter properties with the LIGO, or Laser Interferometer Gravitational Wave Observatory, and the Virgo gravitational wave observations. Professor Reed co-chaired the LIGO-Virgo Binary Neutron Star Sources Working Group from 2014 to 2016, and was part of the team awarded the 2016 Special Breakthrough Prize in Fundamental Physics for the discovery of gravitational waves. She co-led the extreme matter team of the LIGO-Virgo-CAGRA collaboration from 2016 to 2022 through the first discovery and analysis of gravitational waves from a neutron star merger. She has held visiting positions at the California Institute of Technology and the Carnegie Observatories in Pasadena. She chairs the advisory board for the North American Nanohertz Observatory for Gravitational Waves and served on the Scientific Advisory Committee for the Australian Research Council Centre of Excellence for Gravitational Wave Discovery. She was elected a Fellow of the American Physical Society in 2019. If you have any questions during this talk, please type them into the chat or the question and answer dialog box. At this time, it is my great pleasure to introduce Professor Reed.
Hi everyone. So I'm very happy to be here today. I'm very excited to be able to tell some of the story of the first years of gravitational wave astrophysics to a broad number of people. And so I'll be telling a very overview picture of what we're learning about the universe with gravitational waves. And I want to make sure that it's clear that this work is done with a collaborative effort. So I'm at the Nicholas and Lee Begovich Center for Gravitational Wave Physics and Astronomy when I'm at Cal State Fullerton. And a lot of what I'll be talking about has been done both with the LIGO-Virgo-CAGRA collaborations, which are the gravitational wave observatories that are currently taking data. And I'll also tell you a little bit about future prospects with Cosmic Explorer, which is currently being funded by the NSF, the National Science Foundation in the United States, to develop future observatories for gravitational wave astronomy. I do have, I think, the chat open for the Q&A, so do feel free to ask questions as I go. I may leave them till the end if they don't sort of fit into what I'm talking about, but I'm happy to try and make things clearer if they don't kind of hang together as I'm talking about them. So with that, let's get started. So what do I want to talk about today? So the first thing that I want to share is some of the big picture idea of gravitational waves. So gravitational waves are a prediction coming from fundamental physics of our universe, how we understand the world around us in terms of space and time and matter and energy, and they come from Einstein's picture of gravity. So you've probably seen some of this kind of illustration before. The classic picture is that matter tells space-time to curve, And in return, when we move through space-time, our paths are shifted by the presence of matter around us. So this explains orbits. It explains how light travels through the space and time around us. And for 100 years after Einstein formulated this first theory of gravity, we've understand its implications by looking at the messages of light, by seeing the orbit of Mercury, by watching the paths of stars deflected. So we've understood that space and time are curved, but we've understood that by looking at light. So this changed just about 10 years ago, September 9th, 2015. And what happened was that the stretching and squeezing of space and time, the curvature of space-time, dynamically altered the fabric of space-time around us here on Earth, all across the Earth, in a way that we were first able to record on that day. So the effect here is an artist's illustration that's representing how space curved around the Earth at that time. The scale of the effect is vastly exaggerated, so this isn't something that you're going to be able to notice, but it's something that we were able to record at that time with the two LIGO observatories. So there's one in Hanford, Washington, one in Livingston, Louisiana. And these are L-shaped facilities with 4-kilometer-long arms that extend perpendicularly in two directions. And they're carefully measuring the distances along each of these arms to record the signal that passes through them from some distant astronomical event. Now, since that first 2015 discovery, we've also had the Virgo, the European Gravitational Wave Observatory, which is in Pisa, in Italy, as well as the Cagra facility, which is underground in the Kamioka Mountains. And they've all been working together to share observational data, which is important, it turns out, if you want to understand the most possible from these astronomical events, to measure this stretching and squeezing of space-time and use it to learn about the universe. So most recently, about a week ago, there was a public alert from the LIGO, Virgo, and Cagra scientific collaborations. It's the 203rd alert since 2023. And so although you maybe didn't notice this, at that time, space around you wobbled just a little bit in a way that was consistent with a merger of black holes, a distance of around 2 billion light years. So light that are gravitational waves that had been traveling since half the natural history of the Earth. And this public event also came with a sky map. So you try and map the sky similar to the way you might make a map of the Earth. And here was the point on the sky where this event was coming from. So what this kind of signal looks like, how these observatories actually measure this, is they're using laser interferometry. They're looking at interference patterns in laser light. And this is a sort of a simplified cartoon on the left, but what's happening is they're measuring the change in space, the distance along one direction compared to the other. And when that wobble passes through the Earth, all the gravitational wave interferometers shift the two arms relative to each other a little bit. And the gravitational wave strain that we measure is something called, strain. And it tells us how much the gravitational wave signal has shifted the length in one of the arms compared to the other. So one arm is getting smaller, one arm is getting longer. And when each time, one of the arms gets longer, that's a little positive strain, positive change in length, negative change in length. And we have this oscillation coming through which is an up and down ripple in the distances between these floating arms, and that's our gravitational wave. So I mentioned that the scale of the effect was vastly exaggerated before. The 4-kilometer long LIGO interferometers that measured the first gravitational wave, this strain shown here, the fractional change is about 10 to the negative 21. So that's like the same as a distance change, the width of a human hair in a measurement to the distance of the nearest star. So incredibly tiny effect, not something you're going to notice without these kind of custom-built facilities designed to record this kind of perturbation. Okay, and the oscillations, these up and down waves that we're measuring on Earth, are actually in the audio frequency band. So I can play you some slightly cleaned up data recorded by the interferometers in 2015. And that thump was the collision of black holes. Okay, so I'm talking about black holes. I'm talking about black hole mergers. So let me tell you a little bit about what black holes and neutron stars are and what they're going to tell us about the universe as we observe them in gravitational waves. So the reason that the black holes and neutron stars that LIGO, Virgo, and Cagra are looking to observe are going to be black holes and neutron stars that are formed in supernova, in core collapse supernova. And this one of these was famously observed in 1987 from the death of a massive star in the Large Magellanic Cloud, so nearby a small galaxy cloud. And this supergiant, which had at the time a mass about 20 times the mass of the sun and was in the death throes of stellar evolution. So it had expanded to this huge size. So right in the center of this yellow glow here is our sun, 1 solar mass. The supergiant was 20 times the mass, but also hugely puffed out by the dramatic nuclear reactions that were powering the core of the star as it ran out of its initial type of fuel. So if you looked at this supergiant star in the sky in 1987, you would see a sudden huge flash or long time flash. There was the supernova resulting from this. And it was one of the astronomical triumphs of the century to observe this kind of event. Now, if we look at this event today, we see kind of the aftermath of this kind of massive explosion. We see in the center of this Magellanic Cloud, this expanding rings of glowing gas and dust that were lit up by the supernova and are slowly being excited by all the emission from the dramatic event. And at the core of this, it's kind of right now obscured by dust and the leftover mass of the stellar explosion. But the current observations of this supernova remnant are consistent with somewhere in the core here, this incredibly energetic source that is called a neutron star. So one of the reasons we're pretty confident that this is going to be a neutron star is we've seen this kind of event before. Kind of a while before. So there was a supernova observed in the 1054 CE. And if you look at the nebula in the sky left over after that event, this little bright point right here is something called also the neutron star. So these are something that is a collapsed core of a very massive star that's exploded some time ago. And if we work out from the ways that we see neutron stars in our galaxy, we can figure out that these stars from, say, orbits with other stars, they have masses somewhat more than the mass of our sun, but they're incredibly compact. So this is one model which has the radius, the order of 12 kilometers. So I've superimposed a neutron star here, ignoring its gravitational effects over the Facility for Rare Isotope Beams campus. And you can see the Great Lakes here behind it. So it's sort of the mass of our sun compressed down to the size of a small city. So neutron stars are not the only leftover collapsed stellar cores of dramatic compactness like this, a huge amount of mass compressed into a smaller space. If the star is too big, bigger than 20 solar masses, if the initial star is even larger, when it collapses, the core is so gravitationally impelled towards inside itself, propelled inwards onto itself, that the matter that supports the neutron star isn't enough to keep it from continuing its collapse. So the larger stars with larger cores will potentially form black holes. So this is a 62 solar mass black hole. It's more the size maybe of Iceland. And so these black holes are larger than the neutron stars, but that's only because they are so massive. A black hole with a mass of around 2 solar masses would be smaller than this neutron star, but the mass and the radius scale together for black holes. So bigger black holes, bigger size of object. I'm showing the black hole here as just sort of this black object. That's marking the size of the black hole as its horizon. It's not a physical surface like you would have with a neutron star, but it's a sort of point of no return for light that tries to pass nearby this black hole. If it crosses that horizon, nothing can ever escape again. So that's another prediction of curved space-time as our theory of gravity. So we want to see these objects in gravitational waves. And to do that, you need these very compact stars, because what you're going to need is changing mass that changes very dramatically with a lot of mass moving very quickly. And one of the ways to do that is orbiting stars. So if you see, for example, 2 neutron stars orbiting each other, I want to take a minute here and look at this pair of orbiting stars and think about what the gravitational pull, just like a Newtonian gravitational pull, would feel like from this object. And so, of course, you would be kind of following towards that. We subtract off that average gravitational effect. But what you would feel here is that when the stars are to the side, the pull would kind of be a little bit to the side. And when they're lined up, it's more to the middle. And what the change is going to do is give you a slight acceleration outward relative to when they are right on top of each other. So this is the kind of system that's going to emit a gravitational wave. Anytime you have a time-varying motion of mass across your line of sight, the gravitational pull you feel is going to change. And in a relativistic theory, like Einstein's theory of general relativity, you can't know that instantaneously. There's no action at a distance. So the effect in the space-time from the changing gravitational fabric of space-time around these 2 objects is going to ripple out. And the ripple that we see is going to be this gravitational wave effect that's stretching to the side whenever the 2 stars were side to side, and pushing inwards relative to the average when the 2 stars were lined up. So our gravitational wave observatory here sees the relative stretching and squeezing of one arm relative to the other in a way that's going to track the dynamics of the system that's setting the gravitational wave up far away. So this is how we can interpret a gravitational wave. This is, again, the first observation of gravitational waves. And here's a simulation of 2 black holes seen by the way they would affect light behind them, orbiting around each other. And as they orbit, we're going to get a stretch and squeeze, and say every time one of the black holes goes across the top, we would get one of these upward strains. And then as they orbit towards each other, the strain gets faster in its oscillation, it's higher frequency. And then at the end of the merger, the 2 stars, or the 2 black holes here, merge together into a larger black hole and settle down into something that doesn't emit any more gravitational waves, because there's no time varying change in the mass across the line of sight we see. So when we observe a gravitational wave pattern like this, we see this increase in frequency, we see this truncation at the end, and we can match that pattern to a model we have of how two black holes in spiral merge and interact with each other somewhere in this galaxy, a billion or so light years away. So here's sort of just a heuristic example of how this works. You first kind of fit the gravitational wave frequencies by changing the mass of something that would predict it. You can also then figure out the distance by changing the amplitude of the sound, of the signal. So the farther away it is, the more the amplitude of the wave falls off as it ripples out in space from the source. And we can estimate from what system of that mass would start out producing as a gravitational wave strain, how far it traveled to produce the strain we observe today. So this is how we get information about things like mass and distance. And so when we measured that first gravitational wave signal, we knew that it was consistent, at least, with two black holes, each around 30 times the mass of the sun, orbiting each other, colliding together, merging into a single black hole. The first one we observed was about 1.5 billion light years away, and it followed the model predictions of Einstein's theory of relativity. So through this, we have our new way to understand the universe. And not only do we learn about the fundamental physics of black holes and general relativity, but this is also telling us about the kinds of stars that went supernova earlier in our universe's history to produce the masses of black holes that we can see today. So 30 solar masses was actually a bit of a gravitational wave surprise. That was larger than people were expecting the black holes produced by supernova to be. Okay, another big event in gravitational wave history was a little bit later. This is August 17th, 2017. And this was neutron star observations. And so the neutron stars, I talked about how the frequency pattern depends upon the mass. Well, the neutron stars are much lower mass than the black hole. They're smaller. And so they are going to orbit closer and closer together. The frequency is going to get higher and higher. And so we see an audio frequency that's again in audio, but now high enough frequency that you can hear the frequency change as the stars orbit closer and closer together. Now, these are frequencies, audio frequencies of around 100 hertz. So that means that those stars were whipping around each other 100 times a second to stir up the gravitational wave that we hear at this frequency. And then you notice there something different about the gravitational waves from neutron stars, and I'll show you with this simulation from David Ruggici here on the lower right. They're not only curved space-time, that's shown on the bottom here, like we saw for the black holes. We also have the interaction of matter. So this is a magnetohydrodynamic simulation of general relativistic matter as the two stars collide. And you see that here in this simulation, the two stars collapse to a black hole, and they set up these jets in dark blue that were observed eventually to launch gamma radiation in the two directions above and below the orbit. And this is the gamma ray burst we observed shortly after 1708-17. But that's not the only thing that a neutron star merger does that's different. So I can just sort of show this again. So there's the curvature of space-time. There's the orbit of the stars that's deforming the space-time and stirring up the gravitational waves. And as they collide, even before they form that jet, you see that matter is getting flung out into the universe around them. And that matter also has a way of producing light. So not the high energy gamma ray light, but optical light left over from the afterglow of the events. And this was first seen, or so this was used to find the galaxy that hosted 1708-17, the neutron star merger, by this new flash, this new pulse of light, and its days-long fade from blue to red. It was characteristic of the glow of the elements being produced as this neutron star matter flung out into the universe and slowly decayed into matter like we see around us today, which I'll come back to in a little bit here. So this one was a bonanza. There was papers, I think, that had maybe most of the people in astronomy collaborating to interpret this kind of event. We learned that the gamma ray bursts were, in fact, these particular kinds of gamma ray bursts were caused by neutron star mergers. This was a leading theory, but this was direct evidence that was the case. Because 144 million light years away, these gamma ray bursts and the neutron star chirp were so close together, the gap between them is what we think is the time needed to launch the gamma rays. We can measure that gravity and light travel at the same speed, which is another prediction of Einstein's theory of relativity, of general relativity, but that's something that tells us a lot about the fundamental physics of gravity. We confirmed the expansion of the universe because as the universe expands, it shifts the colors of distant galaxies towards the red by the stretching of the light traveling through an expanding universe. So that red shift from this galaxy and the distance from the fall off in the gravitational wave amplitude measure how the universe is expanding in a way that confirms previous observations with things like supernova and pulsing stars. We saw neutron star mergers produce new elements. That's that afterglow that illuminated the galaxy that we found this kilonova in. And we learned that neutron stars are compact, which is what I want to tell you a little bit about next, which is sort of one of the things I'm particularly interested in learning from neutron stars. So let me tell you a little bit about extreme matter and how it plays a role in neutron stars and how we're learning about it from gravitational wave observations. So inside a neutron star, I told you that this is more than the mass of the sun compressed down to the size of the city. And so the matter inside it, the structure inside the neutron star is holding it up against gravity in a sort of an extreme version of the way, say, the Earth is held up against just continued gravitational collapse by the properties of the matter, the crust and the core of the Earth. In the outer crust of the neutron star, we have nuclei and electrons like the matter you see around you today. But as you get to higher and higher density, as you go deeper into the neutron star, the compression basically pushes the electrons into the nuclei, and you end up with this neutron fluid above the density of an atomic nucleus in the core of the star. As you go further and further into the center of the star, we're not 100% sure how to model matter at that extreme. So theoretical nuclear physics has predicted that it's potentially better described maybe by the quarks, the fundamental particles that make up a neutron, rather than the interaction of neutrons themselves, or that even just particles of new particles become favorable to be produced in the higher and higher densities at the core of the star. So just as when, say, you take a pencil and you can take that carbon and compress it to a diamond, this is like a more extreme version of that. You compress matter even further and further, and we may produce forms of matter that can't otherwise be seen in our universe. So this is actually something that hooks into, well, among other terrestrial experiments, what we're learning from things like the Facility for Rare Isotope Beams, so FRIB. So FRIB here is letting us go from the nuclei. One here is the density of an atomic nucleus. So the properties of nuclei that come out of the plane of this phase diagram, that describes matter as it behaves under different conditions. So let me talk a little bit about this. So what we have here is a diagram that's showing as density increases or as temperature increases, the way that the fundamental components, the little quarks shown here as these multicolored blobs that form nuclei, behave can change. So if you take a heavy ion collider, like these blue and black lines, and you smash regular nuclei together, you can make them hotter and denser, and you can try and find a place where they transition, or with the Large Hadron Collider, to the kind of conditions that are very hot, but maybe not super dense of the early universe. A neutron star differs from this in two ways. The first way is a way that's being explored by FRIB. The nuclei are more neutron rich instead of having about half neutrons, half protons, like most of the ones in the sort of the less rare forms of nuclei that you can collide. And to understand that, we need some model that can describe the interactions of nuclei around the density of a nucleus. Now, neutron stars are complementary because they're going to a more extreme version of both neutron richness and more extreme version of density. And then they additionally fling out their matter that cycles back down through the exotic nuclei into the nuclei we see this around us today. So when we understand the properties of dense matter in neutron stars, we're understanding something about the way matter behaves that can complement the way that we are able to probe that same interaction with facilities on Earth. So this is one of the fun things we get to do, is to kind of join forces across different areas of physics to understand fundamental interaction of matter. So how this works in practice for neutron stars. So we can kind of pare down a lot of what we're trying to learn to something that's called an equation of state. And it's basically the density at different densities inside the star as you go from the crust to the outer core to the inner core. At a given density, how much does matter resist compression? What's the pressure that the matter will exert to support itself at a given density? And I'm just showing you a handful of models, and they have different types of behavior in the pressure density curve that tell us about how the form of matter might change or how particles interact at different regions within the neutron star core. Now, depending on which of these models you choose to describe dense matter, you'll get a family of neutron stars. So each, say, crust core model here maps onto one of these lines here, and these lines tell you how massive can neutron stars be and how big is their radius. So two ways of saying large. Now, you can see now that if you can measure, there's two ways that you can kind of use this to learn about neutron star matter. One of the ways is if you measure a really massive pulsar. So this is the most massive pulsar measurement. A pulsar is a neutron star that pulses in radio waves. And by the properties of the radio waves coming from the star orbiting another object, you can figure out the mass of the objects in this system. Now, because we have this massive star, a model of neutron star matter that doesn't produce stars that big can be disfavored. So that's one way to learn about it. But the thing that we're going to try and do with neutron star mergers is actually look at something related to the radius of more low mass stars, the ones that we've actually observed. So you can see here that depending on the equation of state, depending on the properties of dense matter, we have different radii for these neutron stars. And what this means for gravitational waves is it changes how much the companion distorts the star very dramatically as the two stars orbit. Now, depending on how much the companion distorts the star, will change the way the two stars orbit and merge. And because the gravitational waves trace the dynamics of those orbits, by observing the gravitational wave pattern, we're going to be able to tell how much distortion would be allowed before the star would completely disrupt or merge or end the gravitational wave signal. So this is how this works. So we have this parameter that I'm just going to say is characteristic of the size of the neutron stars. So the brightest one here, the yellow one here, is something like 2000 for this parameter. And then the black one is 0, or the dark blue one is 0. That's like a black hole. So because of the distortion of matter in these neutron stars, as the stars approach each other, for the final orbits that we observe in the gravitational wave signal, we'll see that these two stars start to distort and eventually collide together, ending the orbit with an increase in the distortion and an earlier merger for depending on how large the stars are. So when we observe the gravitational waves and we try and match our model of the gravitational wave signal to the data recorded by the interferometers, we can try and figure out which of these characteristic parameters best describes the final orbits. So this is like the last 40 milliseconds of a minute-long signal in the gravitational wave data. So you need better and better, with better observatories, we'd be able to do this a little bit better. But so far, we've observed 2 double neutron star mergers, and each one let us rule out parameter values that are more than around 1,000. So this is a characteristic mass. So for an equal mass system, the 2 gravitational wave sources we saw had one had sort of more heavy, massive neutron stars. One had lighter, less massive neutron stars. And in both cases, we learned something about how deformed those stars could get in their final orbits. For the more massive one, it turns out that the limit we set from gravitational waves wasn't very informative because it agreed with the range already predicted by almost all the models for neutron star matter that you could consider as realistic. But for the first merger we observed, for 1708-17, we find that the data that we observe in gravitational waves doesn't allow the stars to distort too much. And for example, models of neutron star matter, which tend to have larger radius, so anything above orange, is disfavored by the gravitational wave model. It prefers stars that have radii of 11 or 12 kilometers. So this is going to combine with those radio pulsar observations, other observations of neutron stars in our galaxy, information we're getting from the nuclear experiments on Earth, and it sets stringent new requirements on models of dense matter and limits on the structure of neutron stars. So why might you care about this? Well, one of the reasons we care about the neutron star matter, not only because of its ability to test our ability to understand matter in its densest state, is that dense matter plays a role in a huge array of interesting sites in transient astronomy. So when we see neutron stars burst in our galaxy, when we see short gamma ray bursts like the one associated with the first neutron star merger, when we see supernova, or when we see the black holes and neutron stars that they produce, the core of these events is dynamically driven by dense matter above nuclear density, where the equation of state plays a role. Gravitational waves are also going to tell us something about how often each of these events have occurred, what kinds of supernova have made black holes, and also when these neutron star mergers actually happen. And so, for example, this is telling us something that, for example, iridium, there's one of the elements in our periodic table, is made in the merger of neutron stars. So when we understand how often neutron stars merge, how much matter they fling out, which depends on their dense matter properties. We'll learn from gravitational wave astronomy how much iridium they put out into the universe. So the last little thing that I wanted to talk about was where we're going from here, a little bit about the future of gravitational wave astrophysics. So since 2015, we've been increasing the sensitivity of LIGO, Virgo, and CAGRA, the ground-based facilities. And so up to 2020, we have these 90 events. Actually, sorry, this guy right here, that was measured in 2023. But we have these events where the masses are known roughly from the gravitational wave observation, and we see 90 systems, mostly two black holes merging, some neutron stars with a black hole, and those are our two double neutron star events. So then the events we have on this chart are only the events up to 2020. And if we take observing time of the gravitational wave observatories and number of candidates, we see that as the detectors have improved, our rate of events gets faster. So from the observing run with most of the outputs seen here, these first 90, that was ending in 2020. The new observing run that started in 2023 has detected more than 200 events, and at a rate roughly double that of the previous observing run. Now, of those announced events, they're almost all black holes or neutron stars, a couple of neutron stars with a black hole. So sadly for me, there's no more double neutron stars to talk about directly yet. But they're telling us about things like the masses of neutron stars, which again feeds into our understanding of neutron stars in our universe. Now, compared to those first 90 events, so I'm going to give you plots of the reach of the detectors as a function of the total mass and the redshift out to which we can see. So our first black hole binary was at a redshift of about 0.1. Our first BNS was really nearby, a redshift of 0.01. And then all the neutron star black holes were in the middle, and most of the events were far away, close to the limit of where we can reach. And that's because as we increase our sensitivity, as we see further into the universe, we expect to see greater populations of merging events predicted by our current understanding of how often these things happen. So as we upgrade the facilities in this decade, we'll start to see a huge number of black holes and start to see more of the population rather than this sort of tail end of the events that occur in our universe from the gravitational wave observatories. Our goal upgrade for the current generation of facilities is to make a dent into the populations across all source classes in the early 2030s. But scientists don't want to stop there. So we have plans in place right now or being made right now to build new facilities in the future for ground-based gravitational wave detection. So in Europe, there's plans for a 10-kilometer underground triangle. And in the US, there's plans for 20-kilometer and 40-kilometer L-shaped surface observatories that are on the roadmap for funding agencies to design and build, starting with site selection kind of this decade and building and taking data in the mid 2030s if everything goes smoothly. So I wanted to show you an artist concept of Cosmic Explorer that comes from Cal State Fullerton, where my colleagues there are working on trying to find good site locations for the Cosmic Explorer observatories, because I want to show you a little bit about the scale. So remember, LIGO and Virgo are around 3 to 4 kilometer arms in either direction. Here's Cosmic Explorer, where our goal would be to build a facility 10 times the length. I'm going to go back to my one equation for this plot. So gravitational waves make strain. They change the relative distances between objects. Interferometers measure the change in that relative strain. So our gravitational waves are going to produce the same H, but in our new interferometer, L is 40 times or is 10 times the size. So that means our change is also going to be 10 times the size. And that's how one of the key reasons we can make such a game-changing increase in sensitivity with this kind of facility. So here's our punchline plot for Cosmic Explorer. And this is a similar cosmic reach to what the European Einstein telescope is aiming to have capable. So again, we have our first few events, the first neutron star merger, the first binary black hole. Here's the largest binary black hole masses that were announced with the third observing run. And with cosmic reach, there's two things that are really interesting. Anything that we would be capable of seeing today, we would see really, really loudly. We would be able to have exquisite sensitivity to test our understanding of matter, space, and time by observing signals like the ones we've seen so far with a detector that's much more powerful. But the other thing we'll get to see is to see across the universe. We'll see not only one gamma ray burst with a gravitational wave signal, but any gamma ray burst that can be identified will have potentially a gravitational wave counterpart that can go along with it. We'll be able to see the entire cosmic population of black hole mergers and neutron star black hole mergers, at some masses even going back to the remnants left over from the very first stars. Formed before the first generation of stars formed after the earliest stages of the universe. And if there are primordial black holes left over by the way our universe formed, which is very chaotic and dynamic space and time fluctuations, those black holes would also be present in the reach of these facilities. So I'm gonna leave off with sort of a conceptual note that when we first saw gravitational waves 10 years ago, that was our instruments just barely sensitive enough to measure the loudest signals passing through Earth from astronomical events. So that was our Galilean observations, the first instrument that was just able to see beyond previous capabilities and revolutionize our way of seeing the universe. So here's an example from March of what telescopes can do today. This is the DESI collaboration releasing a chart of galaxies. Each dot is a galaxy and Earth is right at the center here. So the structure of the universe observed in galaxies charting over 11 billion years of light travel time to get to this observing point here on Earth. So we've gone from first observations to seeing across the universe. One of the cool things about gravitational waves is we could go from the first observations to seeing across the universe in 100 years. So that's a very exciting prospect for a new tool to see the universe. I'll stop here. I'm happy to answer questions. And thank you all very much for your attention.
Thank you very much, Professor Reed. That was a beautiful talk. Really, really interesting stuff. And I see there are a couple of questions in the question and answer section. So there's a question from Roger Hilton. Is there an analog to the microwave background radiation for gravitational waves?
Yes, absolutely. So yeah, so you might have noticed here, this is the cosmic microwave background radiation left over from the earliest stages in the universe. So there's a few ways to think about this. So the dynamics of this early stage of the universe. So one signature might be primordial black holes, but you might also be interested in the echoes of the dynamics rippling through space and time itself. We do look for this. The idea is this would be like kind of a hiss, not a single resolvable signal, but kind of a background set of fluctuations. So we look for kind of what's called a stochastic background of ripples in space-time that are consistent between the observatories, so astrophysical, but don't have a particular pattern, but just an excess amount of fluctuation compared to what you'd otherwise expect, like more correlation between the different facilities. So yes, we do look for those. Well, one I can maybe we have measured a stochastic background with another form of gravitational wave astronomy. However, we think that that one is a background of supermassive black hole merging, not early universe, but the principle is sort of the same.
Very, very good. There's a question from Olivier Massot asking, what is the theoretical model of the atomic nucleus as these nuclei form neutron stars? Would the ultra-dense matter be called nucleonic molecules?
Right. So the interesting thing about the ultra-dense matter is that because the density is so high, what you end up having is you start with atomic, potentially atomic structures or something like atomic structures. So in the outer layers of the neutron star, you can have what's called sort of pasta phases. So structure within the fluid that has shapes and things like that, which you might make an analogy to chemistry in that sense. The overwhelming compression of gravity at the core of the star turns this into just a soup or a fluid of neutrons or even quarks interacting directly with each other that doesn't really have space for structure like molecules, but it's just like kind of like dense neutron or quark fluid where we don't think there's any kind of anisotropy or everything kind of turns into a indistinguishable mush because it's at such a high density that there's no real at least as far as theory can predict, no real structure that can survive. Not sure if that 100% answers your question, but hopefully it gives you something to think about.
There's actually quite a lot of questions now. We'll take a few more. Roger Nguyen asks, are there any practical experiments to directly generate or manipulate gravitational waves, or is gravitational wave research largely observational?
Yeah, so I didn't give you many numbers to tell you about this, but it turns out that like one of the reasons that we see gravitational waves only from these very extreme systems is that, if you take a purely classical picture of gravity, like I would set up gravitational waves just by doing this, by waving my arms around, like that's changing mass. But the amplitude of these is many orders of magnitude below that 10 to the minus 21 relative strain that our loudest gravitational waves observed would see. So people periodically try and think up ways to try and produce a measurable gravitational wave, but so far that's been beyond our capabilities. Of course, when Einstein wrote his paper on gravitational waves, he said that they have, under all circumstances, a completely negligible amplitude. So, ask again in 100 years.
That's very true. Thank you. There's a question from Mark Urban Lorraine, who asks, how long does it take from the time of first detecting binary black holes orbiting until they merge?
Yeah, so I think for black holes, yeah. So this is, for this event, they kind of emerged from the background noise, a third of a few, sorry, confused suddenly by this. Yeah, a tenth of a second before they merged.
Okay.
For the neutron star merger, we actually have relevant data in band for about 60 seconds. So, but they are quick in the sweeps through the audio band that we're sensitive to with LIGO. The events themselves, the orbits have been happening for millions of years, probably.
Very good. There's a question from Andrew Clark who asks, the frequency of the gravitational waves is a function of the binary orbit speed. When they merge and collapse and a tremendous amount of mass is converted to energy, does that loss of mass appear as a major gravitational wave?
Yeah, so when we make the full models we use to analyze the data, we use something like this supercomputer simulation shown here to track not only like the orbit, but this merger process, which you'll see here in a little second. And this final black hole here has less mass than would be predicted if you just summed the masses of the first two events, because about 2 or so solar masses has gone out into energy. So that mass loss changes the prediction of the signal. And when we test gravitational theory with gravitational waves, one of the things we check is that if this end settling down of the final black hole is consistent with how much energy loss we expected from the previous merger stages.
Okay, very good. There's a question from Bibik Gautam who asks, what do we expect about the gravitational wave observation of a core collapse supernova, and what implications would it have to the state of nuclear matter?
Yeah, that's a great question. So unfortunately, we don't have let's see, as clean an ability to model the dynamics of a core collapse supernova compared to something like black holes, which in a sense are very simple systems. They don't have a lot of knobs to tune when you choose what you simulate. So we think that if a core collapse supernova occurred in our galaxy, we would be able to see it. And if we measured it with something like Cosmic Explorer, we would see it with high fidelity. That would act as kind of a burst of gravitational waves at high frequency, where we wouldn't have probably not the same ability to in detail track some cycles because it's a more of a dynamic event. What we could say something about is what frequencies of matter oscillation were present in the core collapse, and that would tell us something about what drives the dynamics of the explosion that we later see in light.
Okay, we'll take one last question, and then people can answer questions privately after the public session's over. So the last question is from Joel Quabia, who asks, can we analyze the gravitational wave data to calculate the distance from the Earth where the events occur, and how far can we see now?
Right, yes. So that's exactly, you need sort of two steps. So you use the frequency pattern to tell you what the masses are, and then we have predictions what the starting amplitude is for a given mass, and then the fall off with distance. So for example, for this first example, we fit the distance by kind of changing the amplitude of the signal. There's some degeneracies with like whether the orbit is face on or tilted and things like that, but that gives us an idea on the distance. Okay. And then, where am I? Yeah, so we're a bit better than this now, but we can see, how do I convert redshift to distance? So that was the first BBH, which is around 1.5 billion light years away. It's a little trickier to go redshift to distance if you go further because the universe is expanding, but let's just call that right now we can see roughly double the distance of that first BBH.
All right, well, thank you so much, Professor Reed. That was a super interesting talk, really well delivered, and thank you for answering so many questions. So I would like to thank everybody for joining us. Have a great rest of your weekend. If you would like to hang around after the public portion, you're welcome to do so. And I'll see everybody else later.